So I'm going to be talking about the turbulent mind of Van Gogh and how the turbulence within his mind contributed to some of his most well-known pieces, especially toward the end of his life. I'll get more into that in a few minutes. Let's look at a picture or at a painting that we've all probably seen before at some point in time. What do you see when you're looking at this? Try not to interpret in this case. What is it that you're actually seeing? Movement. You see a lot of movement here. In the sky especially, you see the quintessential spiral, this vortex here, and this little sub-vortex. Similarly, around the stars, you get these vortices as well. Along the mountains, you get some flow, which is, it looks like it's moving like in congruence with everything that's happening in the sky. You have basically this little town here, which was basically superimposed on the view that he had from his asylum window. You also have flow over the mountains. Everything in this painting seems to flow. So from a mathematical or a physical perspective, one might wonder, like, how closely does especially the flow in the sky mirror real-world turbulence? Because right now, this looks like, if you could describe this right here, turbulence would be a really good word. So we need to figure out, firstly, what is turbulence? Maybe we can somehow, or maybe it's possible to model what's happening in this sky using mathematical models or physical models. But first, what is turbulence? Turbulence is organized chaos. It's a semi-unpredictability of movements in either fluid or a gas. For the sake of this talk, we're going to be talking in terms of fluid dynamics because gases basically work like fluids. It's characterized by apparently chaotic changes in pressure or flow velocity. So, like, for example, you drop a little drop of ink into a glass. Because it's moving quickly, it's going to dissipate quickly, and it's going to form spirals. Turbulence must have the following four features. This is absolutely necessary. It must be irregular, i.e. it appears to flow and change almost randomly. There are rules and laws governing how it's supposed to flow and change. At least it's hypothesized anyway. Turbulent flow must also be diffusive. It has to have a mixing or homogenization quality. So it has to look like it's blending several different things, or maybe some of the, like, if you have like water flowing through water, like in a creek or something, it looks like it's blending. Oops. The quintessential feature that turbulence takes is rotationality. You have to see swirls. Sometimes it's hard to see that. Like if someone, for example, is puffing out a smoke of cigarette, you're going to see just random diffusion everywhere. But turns out there are tiny little spirals that are happening throughout that plume. Or if you just let, like, if you ever watch incense burn, you're going to see a stream of laminar flow coming off of that incense, and then it'll start to get all curly. So that is definitely a hallmark of turbulence. And the most important of the four qualities is dissipativity. What is that? In the absence of additional energy added to the system, big vortices break down into smaller ones, and smaller vortices break down even into smaller vortices. And this goes on and on and on until the size of the vortex is so small that the viscous forces at like a molecular level dissipate the energy of the system completely. So you basically have smaller and smaller and smaller spirals until basically the fluid becomes so sticky that you can't really spiral anymore. Okay, and this will continue until the energy in the system is completely dissipated, as mentioned before, by the viscosity of the fluid at the smallest scales. The Reynolds number, the ratio between the inertial forces and viscous forces of a fluid, largely determine where and at what scale a flow becomes turbulent. So usually flows start as laminar. So like the incense burning stick example, what you have coming off of that is laminar flow initially. Because the smoke is moving very slowly at first, meaning very low velocity compared to the viscous forces of the air, it's not going to become turbulent too quickly. However, if you blow on the incense smoke, you just created a huge amount of velocity and increased the Reynolds number, and therefore you're going to have quicker spirals and quicker dissipation. So, case in point, you have this sort of laminar flow here at the bottom of this whatever's burning down here. And then because the Reynolds number is very low, you're going to start to have this twisty-turny vortex, this three-dimensional vortex sort of situation happening a little bit above whatever the heck's burning down here. So you have some sub-vortices here, and then notice that this is a big vortex that's decomposing into a smaller one. So this happens throughout time. You think that like when you look at paintings or something, you have like a big spiral and then there are small spirals coming off of it and smaller spirals coming off of that. In the case of turbulence, this decomposition of big spirals into small spirals happens over time. So this whole thing will decompose into smaller and smaller spirals, especially the further up you move. So how do we model turbulence mathematically? Most gas and fluid flows found in the wild are turbulent in nature. Very rarely do you actually get smooth laminar flow, except in very confined spaces, like water through a pipe, for example, moving very slowly. If you push water through a pipe very quickly, it's also turbulent. So most fluid flows in the wild are turbulent in nature. Go look at a creek, and yeah, you're going to get some crazy turbulence. So how do we model this? The go-to mathematical formula used to model fluid flows are the Navier-Stokes equations. These are partial differential equations. Okay, so what's that? Okay, y'all have taken algebra at some point in time, right? You're familiar with the idea of an equation and trying to solve for x. How many of you have taken calculus in some way, shape, or form? So you guys know what a derivative is. A partial differential equation is an equation with derivatives throughout it in several variables. So you not only have like f prime of x, you're going to have f, quote unquote, f prime of x and y, or x, y, and z. Since you're working in 3 dimensions, you're going to have x, y, and z as your 3 variables. Can't exactly take a full derivative of a 3-variable function, so that's why we call it a partial derivative. But yeah, you can solve these things for the original function. So you have derivatives. The goal is to find the original function that gave you that derivative. So these equations and their solutions are used to determine how particles move in a fluid or a gas. So you basically start with an equation that has velocities, i.e. derivatives throughout it, and different pressure components within the equation. If you can solve the equation, you basically have a trajectory for how a particle is going to move through that fluid. So the Navier-Stokes equations find applications in modeling how blood flows through the heart, how water moves through a pipe system, and to model weather patterns as well. Given sufficiently many initial conditions for the Navier-Stokes equations and for the aspects of the fluid flow, the solutions to the Navier-Stokes equations almost always involve an element of turbulence, at least the interesting ones anyway. So what do the Navier-Stokes equations give us? They give us basically this sort of appearance here. Here's basically a plane wing. You have flow moving this way. The angle of attack on this wing is very, very high. So what you're going to have is a lot of turbulence happening behind here. So what you see is kind of a path or a trajectory for a particle to move along this flow here. So if we hit the angle of attack right here, it'll go over and then somehow end up in this vortex, perhaps this bigger one, or this one right behind the other two. The Navier-Stokes equations can predict, if you have a good enough solution anyway, can predict exactly where a particle is going to move throughout this situation, and given this shape that's impeding the flow of whatever fluid or gas this is. Okay. Any questions so far? Okay, we're good?
Is the turbulence what causes the lift?
Turbulence, actually that's a great question. What causes the lift is the decrease in pressure over the wing. So you can actually, it's a cool little experiment that you can teach like 3rd graders. Take a piece of paper and then hold it like this and blow over it. Don't blow under it. You think if you create pressure underneath, it'll create lift. That will. But if you blow over it, it'll also create lift. So it's the decreased pressure over the wing versus under the wing that causes the lift.
Is being lifted?
Yes. So this is just a wing through an airstream. So in this case, you have the angle of attack being very, very sharp. So you're going to be basically going up really, really fast.
Or you hit turbulence in the air, it's a little bumpy.
That's because, okay, turbulence is the variation in the chaotic changes in pressure or velocity of air movement. So if you have a wind gust, that's turbulent, especially when the plane's heading at n miles an hour through that wind gust. So it's going to create a new pressure system around that plane and cause it to shift suddenly. That's your turbulence. Not necessarily the turbulence behind the wing that is what's causing that shaking that you feel. It could just simply be changes above or below the airfoils or the wings that's going to cause the up and down motion. So when you're talking about turbulence in a plane, it's large-scale turbulence. It's not the little deviations that you get behind a wing. Okay. So the turbulence problem. This is the mathematical perspective of this. The Navier-Stokes equations in 3 dimensions are incredibly difficult to solve, even with high-powered computers. Like you can't just use a pen and paper and solve this thing. That's why actually I didn't list it. It's ugly. And yeah, it would probably take the next hour to describe every little feature of the Navier-Stokes equations. Kind of complicated. So the problem of determining whether or not the Navier-Stokes equations always have a solution given certain initial parameters, in addition to determining whether those solutions are smooth, is an unsolved problem in mathematics. Okay. Given the pervasiveness of turbulence in nature, this problem is one of the most important unsolved problems in mathematics. So you can't solve it using pen and paper. Computers have a hard time solving it given the initial conditions. And we don't know whether or not a solution exists for every single set of parameters that you could plug in. So if you can, and the smoothness property, I'll probably say something about that. But if you can solve this problem, it has a nice little prize attached to it from the Clay Institute of Mathematics, roughly $1 million. So yeah, there are 7 problems in total, one of which has been solved, the Poincare conjecture. And this one is one of them as well. It's like, turbulence is everywhere. So why can't we model it effectively? Why can't weathermen do their jobs right? Sorry if there are weathermen out there. I know you try. Yeah, so can't solve it. Very difficult to do. And you can solve it in very simple, simplistic settings where you make a lot of assumptions that make the equations pretty. So, yeah, smoothness means like if you can find a solution that means you can derive it infinitely. So you can find the second, third, fourth, fifth, sixth derivative, and so on and so forth. Moreover, if you can find, even if we were to find a solution to the problem as stated, this is a fascinating thing in mathematics. If you can find a solution to saying, yes, a solution always exists, in mathematics, you can answer affirmatively to that question without actually providing what the solution is. It's a weird thing. You can say, here, yes, your problem has a solution. Well, what is it? Oh, that can happen. That can definitely happen. So someone might win the $1 million, say, yes, there is always a smooth solution to any Navier-Stokes equation. Sure, awesome. Can you help me find it? Yeah, that can very well happen. So yeah, so even if, yeah, as I mentioned, even if we were able to solve this problem as stated, the answer might not be as helpful to physicists and engineers as we would hope. So we need a workaround. Since the Navier-Stokes equations are often very difficult to solve, engineers, physicists, and meteorologists often rely on statistical methods of Richardson and Kolmogorov. Okay, and they use this, yeah, basically in everything that they do. The statistical models tend to be better than trying to solve the Navier-Stokes equations. Being statistical in nature, the results of these models are often very imprecise at small scales because you can only take finite amounts of data. So like when you, like how many weather vanes can a meteorologist have throughout the country? You can't have one meter by meter. So you have limited amounts of data, and so you have to process all the data points that you have. That can be quite challenging even from a statistical point of view. So at best, we can produce a rough educated guess for how a particle will move and how a fluid will flow. Okay. Why can't we just use supercomputers to process all the data? Statistically modeling the flow of a fluid up to a granular precision for a certain amount of time is computationally and often practically difficult. Practically because you can't have a weather vane every 5 feet. All right, Computers can only work with finite, albeit large amounts of data, especially supercomputers, and they can only deal with approximated measurements of what is currently occurring in the fluid flow system. So you're not going to get, oh, the wind is moving at exactly 38 knots, because that's not how it works in nature, because you can only measure approximations. The more precise you want your model, the more data and computational time you will need. So if you have more data points, you need more computational power. So that takes more time to handle all of that. So when you're looking at a global scale version of a weather map, like the entire planet, that's a lot of data points. Computers have a hard time processing all of that. There's also often unaccounted for variability introduced to the system in question. So if you're looking at like a weather map of the entire country, you're going to have external forces, external pressure systems coming into that weather map and causing more changes in variability and like basically screwing up the entire model. And so you can't you can't control for that. If you look, you'll be like, oh, let's just use a global one instead, solar flare. Like you're going to have heat coming off the sun or something the sun does. It's going to create a weird pressure system on the planet. And there's always external forces at work when it comes to modeling these things statistically. So the big problem with this is like you have all these different issues that are going to mess with your data. And plus, keep in mind, they're statistical. So you're trying to find averages and likelihood, like the most likely path a certain storm is going to take. Like you have a hurricane coming up the coast. The best you're going to have, because you have finite amounts of data and erroneous data at that, is here's your storm cloud, here's where it could go. So, like, yeah, it's like you have the hurricane cone. I forget what it's called, but like the likely trajectory of the hurricane is because it's very difficult to, because you're using statistical models, predict with any kind of accuracy where a storm or a cloud or an airflow is going to go over the course of time. So that's why weathermen are bad at their jobs. It's not their fault. It's just the models that they're using are statistical in nature. So all this to say, it's very difficult to accurately predict how a fluid will move, even statistically, especially in larger systems. So what does this all have to do with Starry Night? Finally. In 2006, physicist José Luis Aragon, hopefully I pronounced that correctly, and his collaborators from the Autonomous University of Mexico in Querétaro were interested to see if there was a correlation between how Van Gogh painted the Starry Night and the turbulence as measured in the statistical models of Kolmogorov. In particular, they studied and measured the luminance of the painting, which is a particular metric for amount of light per unit area heading in a particular direction. The reason for this is luminance was employed by many impressionists of the time to create a sense of motion or even a twinkling effect. The reason you see the spiral in Starry Night is because of the variation in luminance. So they figured, hey, this should match the velocity flow, the velocity flow of the statistical models of Kolmogorov and Richardson. So yeah. What they were able to find is after digitizing a copy of Starry Night, the researchers computed the distribution of luminance fluctuations on a pixel by pixel basis. So they basically scanned in Starry Night, and then they figured out exactly what the probability of pixels sharing luminance at a particular radius from one pixel to another. They created the probability distribution function from that. They found that the probability distribution function of the fluctuations of luminance, i.e. movement or flow in this case, which the fluctuations represent, correspond notably well with the probability distribution function of the velocity differences of a turbulent flow as predicted by the statistical theory of Kolmogorov. So the statistical theory of Kolmogorov basically says, okay, well, if I compare this point to this point in terms of their velocities and figure out their difference, I should be able to predict at smaller scales, because of a universal nature of how turbulence flows, exactly what the velocity should be at a smaller scale and how the turbulence should break down. It turns out that given the lengths and the distribution of luminance in Van Gogh's painting, it models it very precisely. It models exactly what should happen in nature. Is that a fluke? You know, how many of you have heard of the infinite monkeys theorem? Infinite monkeys theorem is if you have an infinite number of monkeys in an infinite amount of time typing on typewriters, they will eventually produce the works of Shakespeare, all the digits of pi, and all kinds of other fun stuff. They'll eventually do that. You think, well, if you have how many billions of people have existed over the course of time, some painter will be able to pull this off. No, he repeated it. In addition to the Starry Night, the researchers also analyzed several other turbulent paintings of Van Gogh, namely the Road with Cypress and Star, Wheatfield with Crows, and for comparison, Self-Portrait with Pipe and Bandaged Ear. The first two paintings possessed a distribution of luminance that exhibits the same characteristics of natural turbulent flow, in accordance with Kolmogorov's statistical theory. The third did not. Interesting thing is when his madness was at its worst, he painted Road with Cypress and Star, Wheatfield with Crows. In a particular state of calm, as he wrote to his siblings, he painted the Self-Portrait with Pipe and Bandaged Ear. So when he was calm and feeling less, out there, he was, what? So what?
He wasn't outdoors either.
He wasn't outdoors?
He was indoors.
Yeah, he was indoors painting the self, yeah. But because he was in a particular state of calm, he did not paint something that models turbulence flow as well, which is fascinating. So when his madness was at its peak, he painted perfect turbulence. Near perfect turbulence. There was another one of his paintings as well that modeled perfect turbulence as well that they studied. They used the exact same statistical analysis on that one as well. So we're going to generalize a bit. The turbulence you see in both nature and the works of Van Gogh are a form of what are called fractals in mathematics. How many of you have seen that? Like fractals before? Cool, most of you. Fractals are a structure, form, or shape that looks the same both locally, small scale, and globally. You look at the whole, it's the same as if you look at a particular part. There's a rule, either statistical or mathematical in nature, that governs the formation of a fractal. Okay. The classic one that mathematicians like to use when describing fractals is the Mandelbrot set. So if you look here, you have this general structure that has these little offshoot lightning things. I don't know what the heck these are technically called. I don't know if they have a name. But if you have this circle here, this one has a smaller circle that mirrors exactly what this big thing looks like. And similarly, you have this little tiny dot here that looks exactly like this whole structure and this whole structure. So it's like nested. You can think of it as like shapeception. Same thing you have all around this entire bubble here. So the part looks like the whole. That's what a fractal is. You also have the Sierpinski carpet. Who'd like that in their dining room? So this is generated by taking a large square, this big white thing here, and then putting a big square in the center and surrounding it by these smaller squares. And then you do for each of these smaller squares, do the exact same thing with these smaller squares. And then for those smaller squares, you do the exact same thing, propagating ad infinitum. So this is a fractal as well, mathematical fractals. You can also use mathematical fractals to form landscapes. In fact, a lot of video games are starting to had used this for, I don't know, the last 20 years. You can procedurally generate landscapes, beautiful looking landscapes using fractals. Fractals also occur in nature often, very often. There are many clear examples of fractals that have a lovely and exact geometry. For example, you have the snail shell here, definitely a fractal. If I zoom in on the center of the snail shell, it's going to look like, if I look at just this part of the snail shell, it looks like most of the whole as well. So if I continue to zoom in, almost ad infinitum, and nothing in nature is really infinite. It'll look exactly like the whole. If the snail keeps growing, it'll continue to produce basically the same shape. Sunflower has kind of the same features here. You have the core of the sunflower, but you can see these spirals that are coming out here in the distribution of the seeds. So these are also fractal in nature. This little broccoli is like, this looks like a machine created that. It's amazing that nature was able to produce that. So you have your main cone of this broccoli, and then you have these little subcones that if you chopped off one of these little guys, it looks like the entire broccoli. So here you have a fern This is like quintessential fractal here in nature. Big frond with little fronds coming off of it. Take each of the little fronds, they have even smaller fronds. So each of the leaves look like yet another fern. Fractals in nature. These are more geometrical examples of fractals in nature. Turbulence is also a fractal. As mentioned before, yes, it's also a fractal, both energetically and visually over time. Okay, so recall that in turbulence, a fluid flow usually starts as a large vortex, which dissipates into smaller and smaller subvortices, where each smaller vortex inherits the energy of the larger parent vortex. It's like it's this conservation of energy. So like you're gonna have a big flow that dissipates into smaller subspirals, all inheriting the energy of the big parent flow. Those are gonna break down even smaller, and the energy eventually will dissipate into friction and heat. So that breakdown of big spirals and smaller spirals, and even smaller spirals, that creates a fractal over time. Turns out that most things in nature take the form of a fractal. Most things. Trees. You have your main trunk. You have your main trunk that supports all of the branches. The branches support smaller branches. And then the smaller branches support the twigs and the leaves. Okay? And the proportion of the trunk to the branch size is also fractal and proportional in nature. So if you have a big, thick trunk, it's probably because you have big, thick branches. And you have thicker branches, that means you have thicker twigs, and so on and so forth. Unless you do bonsai, then you can force that to look whatever way you want. Yeah, trees are fractals. But why don't they look as nice? That's an interesting question. Flowers are mostly fractals. Rocks and crystals. You take a boulder, you smash it. You can be like, oh, it's still a boulder. Yes, it's still a boulder, but the internal structure and how, like, if you know like lines of cleavage and how a rock will actually break if you smack it hard enough, it'll break down the same way every single time you smack the smaller and smaller rocks. Rocks and crystals especially are fractals. Lightning, that looks like a tree, kind of, in a lot of cases. So you have your main lightning bolt, and then the lightning is going to distribute its energy throughout the cloud system. It's just going to keep just splintering. It's fractal in nature. The shape of our galaxy and our solar system is a fractal. You have your sun. Let's look at the solar system. You have your sun. You have planets going around it. Each of the planets have their own planets called moons, and so on and so forth. It's a small system of fractals. You don't have, moons of moons, at least to my knowledge, in our solar system. Our vascular system is also fractal. Starts at the heart. That's the trunk. You have your big arteries that are coming out of your heart, and those break down into smaller and smaller arteries, and so on and so forth, all the way down the capillaries. It's fractal. Cell division and tissue generation is a fractal process. You have one cell turns into two, two turn into four, four turn into eight. The neural networks in our brain, also fractals. You take a neuron, you have branches off of a neuron called dendrites, and then you have networks of neurons that connect to each of the dendrites, and so on and so forth. You just create a system of neurons, and eventually your brain. Many things on the aforementioned list lack apparent geometry of some of the nicer naturally occurring fractals. Why is that? Any ideas? Why are these fractals not as nice? Maybe you don't believe me. Maybe you think these are actually fractals. That's okay. Turbulence. What is turbulence? Chaos. That's exactly right. There's turbulence. An element of chaos. An element of chaos or randomness is to blame for all of this. Why don't trees look like perfect? Dang it. There we go. Why don't trees look like perfect fractals? Why don't they branch nicely like a third grader's painting? It's because everything in the universe does not exist in isolation. It's very likely that something will interfere with the formation and growth or propagation of the things in the aforementioned list. So, for example, you're not going to get the exact same turbulent flow in a creek every single time you see an eddy. Why? Because there are different rocks in the way. Because there's wind. There's things external to the system that are creating chaos. Alas, despite any randomness that may occur, a general pattern of propagation remains. So it still has some structure amidst the chaos. So it's trying to maintain structure and also branching off and enduring the chaos throughout the propagation process. So here you actually see a wood-burnt tree using electricity. So what they did is they took an electrical diode here, I think it was a diode, and then they burnt it. They just sent a huge amount of current into this piece of wood, and then, like lightning, it propagated out and burnt away this wood to make the shape of a tree, and also the shape of lightning, for lack of better terms. So that's chaos amid structure. You have your main structure, big branches creating smaller branches creating even smaller branches. Nature is constantly at war, balancing order and chaos. There is obvious structure and rules to how something should be, but more often than not, something interrupts that process, creating irregularity and intrigue. A skilled artist wages war on the canvas in much the same way, constantly pitting irregularity and structure against one another to create their piece. Perhaps it is in how this war is carried out that determines whether a work is truly magnificent. In the case of Van Gogh, that war was first carried out in his mind. He had this turbulence going on up in his mind, and that somehow got conveyed to what he painted several times. Perhaps his own internal war between order and chaos is what allowed him to produce such an amazingly accurate depiction of an instance of that same battle in the natural world. It is indeed possible. How that happens is up to speculation. Thank you.